Hi everyone, welcome back. In this video, we will discuss the top Spring Boot interview questions and answers for candidates with 10 years of experience. I am going to explain each question to the point and you can answer the same way in the interview. Let's get started. How does transaction management work in Spring Boot? Explain common real-world issues. Spring Boot uses Spring's declarative transaction management. Transactions are usually defined using the AT transactional annotation. When a transactional method is called, Spring creates a proxy around that method to manage transaction boundaries. The proxy starts a transaction before method execution and commits or rolls back the transaction after execution. By default, Spring rolls back transactions only for runtime exceptions. Checked exceptions do not cause rollback unless explicitly configured. A very common real-world issue is self-invocation. If a transactional method is called from another method within the same class, the transaction does not work because the proxy is bypassed. This causes unexpected behavior in production systems. Another common issue is misunderstanding propagation and isolation levels. Incorrect propagation settings can cause partial commits or unexpected rollbacks. Isolation levels impact data consistency and performance. In interviews, experienced developers must explain how proxies work, why self-invocation breaks transactions, and how rollback rules behave. Interviewers expect real production issues, not just annotation names. Next question. How does Spring Boot handle configuration for multiple environments? Spring Boot supports environment-specific configuration using profiles. Profiles allow different configuration values for development, testing, staging, and production environments. This ensures the same codebase can run in multiple environments without modification. Spring Boot automatically loads configuration files based on the active profile. The active profile can be set using configuration files, environment variables, or command line arguments. This is very useful in CI/CD pipelines and containerized deployments. Spring Boot also follows a strict configuration precedence order. Values provided through command line arguments override environment variables. Environment variables override configuration files. Default values are used only if nothing else is defined. In real interviews, candidates are expected to explain how configuration is overridden, how secrets are managed, and how configuration behaves in Docker or cloud environments. Interviewers want to see that you understand externalized configuration and environment separation, which are critical for production-grade Spring Boot applications. Next question. How do you secure REST API in Spring Boot in real production systems? In real Spring Boot applications, REST API are usually secured using Spring Security. The main goal is to control who can access an API and what actions they are allowed to perform. Every incoming request passes through a security filter chain before reaching the controller. In modern REST API, security is usually stateless. This means the server does not store user session data. Instead, authentication information is sent with every request, usually in the form of a token. When a request comes in, Spring Security validates the token and checks whether the user is authenticated. After authentication, authorization is applied. Authorization decides whether the authenticated user has permission to access a specific API. This is commonly done using roles or permissions. Method-level security is often used to protect business logic. In production systems, additional concerns such as CORS, CSRA protection, and password encoding are also handled by Spring Security. Error handling must be clean so that sensitive information is not exposed. In interviews, experienced developers are expected to explain the request flow, starting from the security filter, through authentication, authorization, and finally to the controller. The focus is on understanding the flow, not writing configuration code. Next, how do Spring Boot microservices communicate and handle failures? Spring Boot microservices communicate either synchronously or asynchronously. Synchronous communication usually happens through HTTP-based REST calls. One service sends a request and waits for a response from another service. Asynchronous communication is used when services do not need an immediate response. In this case, services communicate using events or messages. This approach improves scalability and reduces tight coupling between services. In real systems, network failures, slow responses, and service downtime are common. To handle these issues, microservices use timeouts, retries, and fallback logic. Without these protections, one failing service can bring down the entire system. Another important aspect is service discovery and load balancing, especially in cloud environments where services scale dynamically. Monitoring and logging are also critical to understand failures in distributed systems. In interviews, experienced developers are expected to explain not just how services talk to each other, but how systems remain stable when things go wrong. Interviewers want to hear about failure handling, not just communication methods. Next, how do you optimize performance in a Spring Boot application? Performance optimization in Spring Boot starts with understanding where time and resources are being used. One common area is startup time. Spring Boot loads many components automatically, so disabling unused auto configurations can significantly reduce startup delay. At runtime, database performance is usually the biggest bottleneck. Proper indexing, optimized queries, and connection pooling are critical. Without these, even well-written code performs poorly. Caching is another key technique. Frequently accessed data should not always hit the database. Caching reduces response time and improves system throughput. Asynchronous processing is used for long-running tasks that should not block user requests. Thread pools must be configured properly to avoid resource exhaustion. In production systems, JVM memory settings and garbage collection tuning also play an important role. Monitoring tools help identify slow endpoints and memory issues. In interviews, experienced developers are expected to talk about real performance problems they faced, how they identified bottlenecks, and what steps they took to fix them. Next, how do you handle exceptions and errors in Spring Boot REST APIs? In Spring Boot REST APIs, exception handling should be centralized, not scattered across controllers. Centralized handling ensures consistent error responses and cleaner code. When an error occurs, the application should return a meaningful HTTP status code and a clear error message. Business errors, validation errors, authentication failures, and system errors must be handled differently. A global error handler is commonly used to catch exceptions and convert them into proper API responses. This prevents sensitive internal details from being exposed to clients. Validation errors should clearly explain what input is invalid. Authentication and authorization errors should return appropriate status codes without revealing security details. Logging is also critical. Errors must be logged with enough detail for debugging, but without exposing sensitive data. In interviews, experienced developers are expected to explain error design, not just exception catching. Interviewers want to see that you understand how clean error handling improves API usability, debugging, and system reliability. Next, how do you test Spring Boot applications in real projects? Testing in Spring Boot is done at multiple levels. Unit tests focus on individual classes and business logic without starting the full application. These tests are fast and help catch logic errors early. Integration tests verify how different parts of the application work together. These tests load part or all of the application context and test real interactions between components. External systems such as databases or APIs should not be directly used in tests. Instead, mock implementations or test-specific configurations are used to keep tests reliable. Test profiles ensure that test environments are isolated from production. This prevents accidental data loss or configuration issues. In real projects, test execution speed is very important. Slow tests reduce developer productivity and are often skipped. In interviews, experienced developers are expected to explain test strategy, including when to use unit tests, integration tests, and how to keep tests maintainable and reliable in large Spring Boot applications. Next, how does caching work in Spring Boot and when should it be used? Caching in Spring Boot is used to improve application performance by reducing repeated and expensive operations such as database queries or remote service calls. Instead of fetching the same data again and again, the result is stored temporarily and reused. Spring Boot provides a simple caching abstraction. Developers enable caching at the application level and then mark specific methods whose results should be cached. When a method is called for the first time, the result is stored in the cache. On subsequent calls with the same input, the cached value is returned directly. Caching should be used only for data that does not change frequently. If data changes often, caching can return outdated information and cause inconsistencies. This is why cache eviction strategies are important. Cached data must be removed or refreshed when underlying data changes. In production systems, different cache providers are used depending on scale. Simple in-memory caching works for small applications. Distributed caches are used for large systems and microservices. In interviews, experienced developers are expected to explain what to cache, what not to cache, how cache eviction works, and how caching improves performance without breaking data consistency. Next, what is asynchronous processing in Spring Boot and why is it important? Asynchronous processing allows a Spring Boot application to execute long-running tasks without blocking the main request thread. In synchronous processing, the client must wait until the task completes. This reduces system throughput and increases response time. With asynchronous processing, the request is accepted, the task is executed in the background, and the main thread is freed immediately. This is very useful for tasks such as sending emails, generating reports, or calling slow external services. Spring Boot supports asynchronous execution using background threads. These threads are managed by a thread pool. Proper thread pool configuration is critical. Too many threads can exhaust system resources, while too few can slow down processing. Asynchronous processing improves user experience and system scalability. However, it introduces complexity in error handling, logging, and tracing. Exceptions in async tasks must be handled carefully because they do not propagate to the caller. In interviews, experienced developers are expected to explain why async is needed, how thread pools work, and what problems async processing can create if not designed properly. Next question. How does Spring Boot interact with databases and what are common performance issues? Spring Boot interacts with databases using abstraction layers that simplify data access. These abstractions allow developers to focus on business logic instead of low-level database operations. A major performance issue in real systems is inefficient queries. Fetching unnecessary data, missing indexes, or poorly designed queries can slow down applications drastically. Another common issue is improper connection management. Spring Boot uses connection pooling to reuse database connections instead of creating a new one for every request. If the pool is not configured correctly, the application may run out of connections or waste resources. Lazy loading can also cause performance problems. Fetching related data unintentionally can result in multiple database calls. This issue often appears in production, not during development. In interviews, experienced developers must explain how database interaction works, why indexing matters, how connection pooling improves performance, and how to identify and fix real database-related performance problems. Next, how do you monitor and observe Spring Boot applications in production? Monitoring and observability are critical in production Spring Boot applications. Without visibility, diagnosing performance issues or failures becomes extremely difficult. Monitoring focuses on system health metrics such as CPU usage, memory usage, response time, and error rates. Observability goes deeper and helps understand why a problem happened, not just that it happened. Logs, metrics, and traces work together to provide full visibility. Logs show what happened. Metrics show trends over time. Traces show how a request flows through the system. In distributed systems, tracing is especially important because a single request may pass through multiple services. Without tracing, debugging becomes guesswork. In interviews, experienced developers are expected to explain why monitoring is necessary, what should be monitored, and how observability helps debug real production issues. Interviewers look for real experience, not tool names. Next, how do you deploy Spring Boot applications in real production environments? Spring Boot applications are designed to be deployment friendly. They can run as standalone applications with an embedded server, which simplifies deployment. In real environments, applications are deployed using automated pipelines. Configuration is externalized so the same build can be used across environments. Environment variables and profiles control behavior without code changes. Applications must handle graceful shutdown, startup failures, and health checks. These aspects are critical for reliability and scaling. Security, logging, and monitoring must be configured properly before deployment. Poor deployment practices cause most production issues, not code bugs. In interviews, experienced developers are expected to explain deployment strategy, environment separation, and operational concerns. Interviewers want to see that you understand what happens after code is written, not just during development. Next question. What are the core principles of microservices architecture and how does Spring Boot support them? Microservices architecture is based on building applications as a collection of small independent services. Each service is responsible for a specific business capability and can be developed, deployed, and scaled independently. The core principles include loose coupling, high cohesion, independent deployment, and decentralized data management. Services communicate with each other using lightweight mechanisms such as HTTP or messaging. Spring Boot supports microservices by reducing configuration overhead and enabling fast service development. Each microservice can be built as a standalone Spring Boot application with its own embedded server. Spring Boot encourages separation of concerns by clearly defining controllers, services, and data layers. This aligns well with microservices, where each service owns its logic and data. Configuration externalization allows the same service to run in multiple environments without code changes. Spring Boot also integrates easily with cloud and container platforms, which are commonly used with microservices. In interviews, experienced developers are expected to explain that microservices are not just about splitting code. They are about designing services that are independent, resilient, and aligned with business domains. Spring Boot acts as an enabler, not the architecture itself. Next question. How do Spring Boot microservices handle service discovery and why is it required? In a microservices architecture, services are dynamic. Instances are created, destroyed, or scaled frequently. Because of this, hard coding service addresses is not practical. Service discovery solves this problem by allowing services to find each other dynamically at runtime. Each service registers itself when it starts and removes itself when it stops. Other services query the registry to locate available instances. Spring Boot microservices rely on service discovery to enable loose coupling between services. A service does not need to know where another service is running, it only needs to know the service name. Service discovery also supports load balancing. When multiple instances of a service are available, requests can be distributed across them automatically. Without service discovery, microservices become tightly coupled, and difficult to scale or maintain. Failures also become harder to handle. In interviews, experienced developers are expected to explain why service discovery is essential in distributed systems, how it enables scalability, and how it prevents configuration-related failures in real-world microservices deployments. Next question: how do you handle inter-service communication in Spring Boot microservices? Inter-service communication is a critical part of microservices architecture. Services need to exchange data to complete business operations. Spring Boot microservices typically communicate in two ways: synchronous and asynchronous. Synchronous communication is commonly done using HTTP-based APIs, where one service waits for a response from another. Asynchronous communication is used when services do not need an immediate response. Messages or events are sent, and services process them independently. This approach improves scalability and reduces tight coupling. In real systems, network failures and latency are unavoidable. Therefore, communication must include timeouts, retries, and fallback mechanisms. Without these, a slow or failing service can cause a chain reaction and bring down the system. Choosing the right communication style depends on business requirements. Overusing synchronous calls can reduce system resilience, while asynchronous communication adds complexity. In interviews, experienced developers are expected to explain communication patterns, trade-offs, and how failures are handled gracefully in Spring Boot microservices. Next question: how do Spring Boot microservices handle data management and database design? In microservices architecture, each service should own its data. Sharing a single database across multiple services creates tight coupling and defeats the purpose of microservices. Spring Boot microservices follow the principle of decentralized data management. Each service has its own database or schema, which allows independent evolution and deployment. This design improves scalability and fault isolation. If one service's database is slow or unavailable, other services are not directly affected. However, managing data across services introduces challenges. Transactions across multiple services are difficult. Instead of traditional distributed transactions, systems rely on eventual consistency. Data duplication is common in microservices. Services may store copies of data needed for their operations. This improves performance but requires careful synchronization. In interviews, experienced developers are expected to explain why database per service is important, how consistency is handled, and what trade-offs exist when designing data models for Spring Boot microservices. Next, how do you design microservices for fault tolerance and resilience in Spring Boot? Fault tolerance is critical in microservices because failures are inevitable in distributed systems. Services can fail due to network issues, high load, or infrastructure problems. Spring Boot microservices must be designed to handle these failures gracefully. A service should not crash or block indefinitely when another service is unavailable. Timeouts prevent services from waiting forever. Retries help recover from temporary failures. Circuit breakers stop repeated calls to a failing service and allow it time to recover. Bulkhead patterns isolate failures so that one slow component does not consume all system resources. Fallback mechanisms provide default responses when dependencies are unavailable. Monitoring and health checks are also part of resilience. Systems must detect failures early and respond automatically. In interviews, experienced developers are expected to explain that resilience is a design mindset. Spring Boot provides tools, but developers must design services assuming that failures will happen and plan accordingly. Next question: how do you design and handle distributed transactions in microservices? In microservices architecture, distributed transactions are challenging because each service owns its own database. Traditional database transactions cannot be used across multiple services without creating tight coupling and performance problems. Because of this, microservices avoid global transactions and instead use eventual consistency. The most common approach is to break a large business transaction into multiple local transactions, one per service. Each service completes its operation independently and publishes an event when it succeeds. Other services react to that event and perform their own actions. If a failure happens in one step, compensating actions are executed to undo previous steps. This approach ensures consistency over time rather than immediately. This design requires careful planning. Services must be idempotent so that repeated events do not cause duplicate actions. Error handling must be explicit, and retrace must be safe. In interviews, experienced developers are expected to explain why traditional transactions do not work in microservices, how eventual consistency solves the problem, and what trade-offs are involved. Interviewers look for understanding of real-world failure scenarios, not textbook definitions. Next, how do you handle API versioning in Spring Boot microservices? API versioning is essential in microservices because services evolve over time while clients may not update immediately. Without versioning, a breaking change in one service can break multiple consumers and cause production outages. Versioning allows services to introduce changes safely while keeping older clients working. In Spring Boot microservices, versioning is usually handled at the API contract level. Each version represents a stable contract that clients can rely on. New versions are introduced when breaking changes are required. Old versions should continue to work until clients migrate. Deprecation strategies are important so clients know which APIs will be removed in the future. Versioning increases maintenance effort because multiple versions must be supported simultaneously. However, this cost is much lower than breaking production clients unexpectedly. In interviews, experienced developers are expected to explain why versioning is necessary, how it protects consumers, and how to manage multiple API versions without duplicating too much logic. This shows maturity in API design and long-term system thinking. Next question. How do you ensure observability in complex Spring Boot microservices systems? Observability means understanding what is happening inside a system by looking at its outputs. In microservices, a single user request may travel through many services. Without proper observability, debugging becomes extremely difficult. Observability is built on three pillars: logs, metrics, and traces. Logs capture detailed events, metrics show system behavior over time, and traces show how a request flows across services. Each microservice must log important actions with enough context to identify issues. Metrics help detect slow responses, high error rates, or resource exhaustion. Tracing connects requests across services so failures can be pinpointed quickly. Correlation identifiers are critical. Every request should carry an identifier, so logs and traces across services can be linked together. In interviews, experienced developers are expected to explain why observability is mandatory in microservices, how it helps reduce downtime, and how teams move from guessing problems to diagnosing them accurately in production. Next question. How do you design microservices for independent scalability? Independent scalability is one of the main reasons for adopting microservices. Each service should scale based on its own workload rather than the needs of the entire system. This requires services to be stateless and loosely coupled. State should not be stored in memory. Instead, shared state should be externalized so multiple instances can handle requests interchangeably. Services that handle heavy traffic should be able to scale without affecting others. This reduces infrastructure cost and improves system efficiency. Data access patterns also matter. Services should not share databases because that creates hidden coupling and prevents independent scaling. In interviews, experienced developers are expected to explain that scalability is not just adding more instances. It is about designing services so scaling one service does not force scaling of others. This demonstrates architectural thinking beyond basic Spring Boot usage. Next question. How do you handle configuration and feature rollout safely in microservices? In microservices, configuration changes happen frequently and must be handled carefully. Configuration should be externalized so services can change behavior without redeploying code. This allows faster fixes and safer operations. Feature rollout should be gradual. New functionality should not be enabled for all users at once. Instead, features can be enabled selectively and monitored for issues. If problems occur, features must be disabled quickly without redeploying services. This reduces downtime and risk. Configuration errors are one of the most common causes of production failures. Validation and clear separation between environments are critical. In interviews, experienced developers are expected to explain why safe rollout matters, how configuration is managed across environments, and how teams reduce risk when introducing changes in large microservices systems. This reflects real operational experience. Next question. Describe a common cascading failure scenario in microservices and how you debug it. A cascading failure happens when one failing microservice causes multiple dependent services to fail. For example, a downstream service becomes slow due to database issues. Upstream services continue sending requests and wait for responses. Their threads get blocked, thread pools become exhausted, and soon those services also start failing. From the outside, it may look like the entire system is down, even though the root cause is a single slow service. Debugging starts by checking system-wide symptoms. Response times increase, error rates spike, and thread pools show saturation. Logs often show timeout errors rather than clear failures. The next step is tracing requests across services. Traces usually reveal where delays are happening. Metrics help identify which service is consuming most time or resources. Once the root service is identified, the fix usually involves adding timeouts, limiting retries, and introducing circuit breakers. This prevents failures from spreading. In interviews, experienced developers are expected to explain not just what cascading failure is, but how they recognized it, isolated the root cause, and changed the system design to prevent it from happening again. This shows real production experience. Next, how do you debug high latency issues in Spring Boot microservices? High latency issues often appear gradually rather than as sudden failures. Users may report slow responses even though the system is technically up. CPU and memory may look normal, making the issue harder to diagnose. Debugging starts with identifying where time is being spent. Metrics help determine whether latency comes from the application, database, or external service calls. Distributed tracing is critical here. It shows how long each service and each operation takes during a request. Often, one slow database query or external API call dominates the response time. Logs are used to correlate slow requests with specific inputs or conditions. Sometimes, latency only happens for certain data sizes or edge cases. Common fixes include optimizing queries, adding caching, reducing payload size, and tuning thread pools. Sometimes the fix is architectural, such as switching synchronous calls to asynchronous processing. In interviews, experienced developers should explain how they move from symptoms to root cause and why guessing without data usually makes latency problems worse. Next question. Explain a production issue caused by misconfiguration and how you troubleshoot it. Misconfiguration is one of the most common causes of production incidents in microservices. A typical example is incorrect timeout, connection pool size, or memory configuration. The application may work fine in lower environments but fail under real production load. Symptoms can include frequent timeouts, connection errors, or unexpected restarts. Logs may show errors, but the real issue is configuration, not code. Debugging starts by reviewing recent changes. If code has not changed, configuration becomes the prime suspect. Comparing production configuration with staging or previous working versions often reveals the issue. Metrics help confirm whether resources are being exhausted. For example, connection pool metrics may show all connections in use, indicating misconfigured pool size. The fix usually involves correcting configuration values and redeploying or reloading configurations safely. Long-term fixes include validation, sensible defaults, and better environment parity. In interviews, this question tests whether candidates understand that many failures are operational, not coding mistakes, and how careful configuration management prevents outages. Next question. How do you debug memory leaks in Spring Boot microservices? Memory leaks are dangerous because they often appear slowly and worsen over time. A service may run fine initially, but gradually consume more memory until it crashes or becomes unresponsive. Restarting the service temporarily fixes the issue, but the problem returns. Debugging starts by observing memory metrics. A continuously increasing memory usage without release is a strong indicator of a leak. Garbage collection logs often show increased frequency without effective cleanup. Next, heap analysis is used to identify objects that are retained unexpectedly. Common causes include unbounded caches, static references, and listeners that are never removed. In microservices, memory leaks can also occur due to excessive object creation from high traffic or improper handling of large responses. Fixes include limiting cache size, cleaning up resources properly, and reviewing object lifecycle management. In interviews, experienced developers should explain that memory leaks are rarely obvious and require systematic observation, not trial and error fixes. Next, describe how you debug a production issue that you cannot reproduce locally. Some production issues cannot be reproduced in development environments due to scale, traffic patterns, or real user behavior. In such cases, debugging relies on observation rather than reproduction. Logs, metrics, and traces become the primary tools. The first step is narrowing down the conditions under which the issue occurs. This may involve identifying specific users, requests, or times when failures happen. Next, additional logging or diagnostics may be enabled temporarily but carefully to avoid performance impact. Feature flags are often used to isolate suspected code paths. If necessary, a controlled fix or workaround is applied to reduce impact while deeper analysis continues. The goal is to stabilize the system first, then fully understand the root cause. In interviews, experienced developers are expected to explain a calm, structured approach to debugging under uncertainty. This demonstrates maturity, responsibility, and real-world problem-solving skills.